Find the maximum value of z. In this problem, the objective function, z, is a linear function of variables x1, x2, and x3. The constraints are linear functions of x1, x2, x3, and x4, where the decision variables x1 through x4 are non-negative. If we convert the problem into standard form, we want to minimize the objective function, so we can simply multiply both sides by -1. Next, we'll convert the constraints to standard form by adding a slack variable to each constraint such that the at most sign can be changed to an equal sign. Now the decision variables are x1 through x4, as well as s1 and s2, where s1 and s2 are the two slack variables, which must also be non-negative. As an initial feasible solution, we'll assume the slack variables s1 and s2 equal 20 and 30, respectively, and x1 through x4 equals 0. For this initial solution, the objective function equals 0, since x1, x2, and x3 all equal 0. Next, we'll use the simplex method to maximize z, such that the constraints are all satisfied. Setting up the network tableau for this problem, the two slack variables s1 and s2 are the two initial basic variables, with values of 20 and 30, respectively. The reduced costs for each variable are shown along the top. This tableau is in canonical form because the right-hand side variables are non-negative, the cost coefficients associated with the basic variables are 0, and the identity matrix is associated with the basic variables. The linear system of equations in this tableau can be written as AX equals B, where A matrix is comprised of the variable coefficients, the X vector are the decision variables, and the B vector are the constants on the right-hand side. The algorithm begins by pricing out, which determines which non-basic variable is next to enter the basis. This involves scanning the reduced costs for the most negative value, which turns out to be -5, and is associated with variable x1. This means x1 is the next variable to enter the basis. If the most negative reduced cost was 0, then the current solution would be optimal. Next, the ratio test is conducted to determine which basic variable will leave the basis. The variable to leave the basis will be in the row I, which has the smallest positive ratio B over A for the column associated with the variable entering the basis. If we assign S1 to I equals 1 and S2 to I equals 2, since 5 is a smaller positive number than 10, then S1 will leave the basis. The ratio test ensures the new basis is feasible. After inserting variable x1 into the basis, the pivot operation from linear algebra is performed, so the tableau is again in canonical form. Pivoting involves adding a multiple of row I to all rows such that all rows in column T equal 0, except row I, which equals 1. For example, looking at the top row, we need to add 5/4 of row I to the top row, so the -5 in column T of the top row equals 0. That is, negative 5 plus 5/4 of 4 equals 0. This operation of multiplying 5/4 of row I to the top row is carried out for all columns. The bottom row will undergo the same operation, except the multiplier will be negative 3/4 rather than 5/4. The bottom row is updated as shown. Lastly, negative 3/4 of row I is also added to row I, such that the pivot element in row I, column T, equals 1. This value of 1 is part of the identity matrix required for that tableau in canonical form. The numbers are updated, and the pivot is complete. At this point, the variables x1 and s2 are basic and equal 5 and 15 respectively. The other 4 decision variables are non-basic and equal 0. The revised reduced costs are shown along the top, and the current objective function value equals 25. Now we return to the first step of pricing out. Since the reduced costs of all non-basic variables are non-negative, we have found an optimal solution. And since these non-basic reduced costs are all positive, we have found a unique optimal solution. The optimal set of decision variables, vector x, is shown, and we confirm the objective function value is 25, as is shown in the tableau. When reviewing the possible solutions, the answer is C.